Okay, so this is the first video from Chapter 10 concerning fluids, and we're going to go through three examples in this. The first example I think is really cool because everybody's heard of the Archimedes Eureka story where he's in the baths of some kind of Greek or Roman town. I think it's Roman, and he's trying to figure out how to figure out if the king's crown is made of gold or not, and he does this little displacement trick to find out the volume of the crown and so forth. Well, this is going to show us specifically what happened. So the question is the crown made of gold or not? And we're going to use specific gravity eventually to figure that out. Okay, so first, what you do is you make some kind of measurement of the weight of the crown when it's not submerged in water. So if we had accurate modern stuff, we'd say that's 14.7 kilograms or something like that. Then you submerge it in water and you weigh it at that point, and it should be lighter because you have the force of buoyancy pushing up on the crown at some amount. So this time it turns out to be 13.4 kilograms. So the question is, if you know those two things, is that enough to figure out what it's made of, or be close, at least have a good approximation of what it's made of? Is it gold or not, for instance? Okay, so we're going to use the notation W prime and W. So W is its weight without water. W prime is its apparent weight when you put it in the water. So I think you'll agree, if you look at this little free body diagram right here, that the apparent weight is equal to W minus the force that the buoyancy is pushing up on it. That should be pretty simple. Okay, so our next step is to think about W and W prime in terms of density. So you just rewrite them. So you say W, well, of course, that's just the mass times gravity pushing downwards like we've always done. But then we can rewrite W in terms of density. So the density of the crown times the volume of the crown, and then there's our G still. Do the same thing with W prime, so you leave your W alone, and instead of writing we're going to put, instead of writing FB, we're going to put the density of the fluid times the volume for that. Okay, so instead of the, what am I trying to say? Instead of the mass of the water, I should say, or the mass of the fluid, we're going to put the density times the volume. Okay, so same trick, nothing sneaky there. So now we've got W and W prime. Now, what we want to do is we want to figure out, we're going to use specific gravity to answer this question. So if we rearrange and divide, we can get it into a form where we know specific gravity. Remember, specific gravity is when you put the density of whatever object you're working with over the fluid's density, and if you want to really come up with a nice number for specific gravity, the fluid you're using should be 1, so it's just divided by 1. So we're using water, so that's the way we're going to do it this time. So that's the trick. We're trying to get P0 over PF. And when we're looking up here, how can we get P0 divided by PF? I think it's not too bad. So first, in the W prime equation, I guess I'll change to blue. Let's see, do I have a blue? Yes, I do. So in the second equation, I'm going to subtract W. So I get this. Right, and then I think I'm also going to, let's see, should we leave this negative here? I think let's just divide the negative through. So we'll have a positive W, a negative W prime if we divide that through, and now we'll get the density of the water or the fluid times the volume times our gravitational constant. Okay, so now we have that. So now what we're going to do is we're going to take this equation, which has PF in it, that should be on the bottom, and the other equation has P0 on it, that should be on the top. So I think that we should divide the first equation by the second. So if we come over here, I'll try to color code it so you can follow me, and we'll say that we'll have W divided by, and that we had was P0 VG, right? And then I'll get blue, and we'll divide it by what we had down there, which was W minus W prime, and we had PF. And look at that, the V and the G are the same thing, so we can just cross those out. And that's exactly what we wanted. Now we have this arranged in terms of specific gravity. So now we can plug in the things. What was our W? It was 14.7. The things, the measurements. And then we have 14.7 down here. Minus 13.4. That was the apparent weight that we measured. And that's equal to the blank over 1. So we can get the density of this object, which since it's over 1, we'll be able to get the specific gravity. So we do a little calculator action right there, and you get 11.3. And then what you should do is you should go in your table. I think we had a table in our book, and look at the different substances. So you should have a table for specific gravity. Sometimes it says density, and then you just divide by 10 to the third. Remember to get specific gravity. Just watch your units. So let's see, 2.7 is aluminum. Iron and steel have a specific gravity of 7.8. Hey, 11.3, that's exactly lead. Uh-oh. I think Archimedes is going to have to tell the king that his crown is made of lead. Gold would be 19.3, so we can see that they're pretty far off. That crown is definitely not made of gold. So that is a pretty cool trick. Nice historical anecdote to go with it. Okay, let's look at another problem. So the next problem we had, I think, dealt with making your own hydrometer. Yeah, right. So this is like making your own hydrometer. We might do something like this in class as part of an experiment, I think. Anyway, we're going to calibrate it and kind of make our own at the same time. So first you have to weigh the flask, the red guy that you're going to make your hydrometer out of. Let's say ours weighs 45 grams. Measure its length. This one's 25 centimeters. And you've got to measure the cross-sectional area. I'm talking about a cross-section like this. If you slice it, and you get that little circular cross-section. So ours is 2 centimeters squared. Okay, so from the Giancoli book, they spend some time talking about how you can look at submerged logs and figure out basically this equation at the end. So this is the important equation, which is pretty significant. It says that the volume of an object and how much of it's submerged in water is proportional to the densities involved. So the fraction, another way to say this is that the fraction of an object that's submerged in water is the specific gravity, because if you look over here, this is what you're going to have for specific gravity as long as your fluid is water. And over here is just like the fraction that you have submerged out of the total object. So this is just the fractional part that's submerged in that water. So that's really nice. It should be pretty useful, and it can help us make a hydrometer here. So first of all, let's use these numbers and figure out the density of the object that we're putting in the water, the flask. So the density of the flask, mass divided by volume, of course, for density. Just put those numbers in. The units line up to be centimeters cubed. Remember, this isn't SI units, but these units right here, grams per centimeters cubed, that's what you want to use if you're working with specific gravity. If you're just working with density and you look in the book, remember they have like kilograms per meters cubed. And remember, you have to do like a division by a factor of 1,000. I think order 3 division to kind of go back and forth. I'm going to leave that to you to kind of figure out on your own by looking at the problems, but just be aware that that's there. So if you're talking specific gravity, it should be grams per cubic centimeters. Anyway, so the way I thought of that is, hey, that's 90% of the 25 centimeters long. So if we take 90% of that 25 centimeters, we get 22.5. These are uniform cross sections, which means we don't have to worry about anything funny going on. So 22.5 centimeters, if we measure up from the bottom and we make that 22.5, that's where we should place the 1, which is a specific gravity of 1. It should be right there. Okay? I'd also like to extend that question. The book asks this as an exercise, but it's a good question. So what if you get, so let's say we put this hydrometer in another substance, we don't know what it is, maybe it's alcohol, or I don't know, soda pop or something like that, and it doesn't float. What if the water level, let's say here's the water level, let's get our hydrometer and say, okay, we put the hydrometer in there, and now here is 1 the one that we just came up with, and that's above it. The question is this substance that we put it in, this alcohol or whatever, have lower or higher density than water? And I think since this dropped down further, you should realize that these marks up here are going to be lower density, so they should have lower specific gravity. If the one mark was up here, then this particular fluid would have a higher specific gravity and hence a higher density. So anyway, I thought that was a neat problem to look at. We'll do something like that in class as an experiment. Okay, one final example for this video is to consider an air balloon. So let's consider we have a helium air balloon. So we have helium gas in this balloon, and we want to lift a 180-pound load. So the question is, how much gas, how much volume of helium gas are we going to have to pump in there? If you remember from the video, at least in the past, producing helium gas is not such an easy endeavor. If you remember, Dewar and Onnes trying to get a supply of helium gas back in the late 1900s. So I think that was like the 1920s, whenever that time period was. It was difficult for them to do back then, and I think it's still difficult today. So we want to know how much do we need to lift that load? Okay. So I've kind of got a free body diagram going here. There's three force factors. We've got the force of buoyancy of the air pushing the balloon up. We've got the mass of the helium times gravity. That's probably a fairly small one. And then we've got that big, I should have drawn this longer. Let's make this a longer vector. The 180 pounds being pushed down by gravity. So there's three things going on. If we want to be able to at least lift off, then the buoyant force has to be, I should say, greater than or equal to those two things that are pushing down, okay? And that's kind of just thinking about Newton's third law a bit, I guess, if you want to be technical. Anyway, I factored out the g for gravity and said, okay, how about that? Now let's just rewrite the mass. Let's rewrite, in fact, everything in terms of densities. So let's see here, get some densities going. So the force of buoyancy you can rewrite as remember it's due to the air, so it's the air's mass, which you could rewrite with density as density of the air times the volume of the air times the gravity. It's like mg for the air. Okay, that makes sense. And then over here in our parentheses we have helium, so we'll do density of helium times the volume of helium plus, we've got just a nice 180 there, so I don't think we need to change anything, times our gravitational constant g. Okay, and the question was how much helium gas do we want volume-wise? Well, we've got a volume in two spots, you can see in the equation. So I think we need to just, solve for volume. So it shouldn't be a big deal. You've got like 1, and if you distribute here 3 terms, maybe I shouldn't have factored that g out. I don't know. It's kind of up to you. So I guess we'll go and find it. I'll write it out for you. Okay, so we have P air. I'm going to write that P. Density, I should say. Is that P? That's not P. I'm saying the wrong thing. That is rho. Rho. You pronounce that rho, not P. You don't want to get confused. So rho of air volume G. I'm going to subtract rho helium volume G, and that's equal to 180 kilograms times G. Now I'm going to factor out my volume, so I get rho for the air minus rho for the helium gas. And I guess those both have a G2. Factor that out, equals 180 G. And therefore the volume is 180. Those G's just cancel. Let's get rid of them right now. Divide them out. 180 over the rho for the air. What is the density of air? If you look it up in the table, you're going to get 1.29. Remember, that's not the specific gravity. This rho right here should not be a specific gravity. It should be in density terms, which is kilograms per meters cubed. So make sure you get the right value from your table. Minus, for helium, you have 0.179 kilogram per meter cubed. So I think that's 160 cubic meters. That's a pretty big balloon that we would need. Okay, hope you found this video useful. I'll probably have at least one more for this chapter. Bye now.